it started with the velocity. So for example, the Vs is completely off. And just it moved and found it. Density is also pretty off, and it gets in there. Although I am not going to say this is perfect. And this is the synthetic gather, full waveform gather, and this is the real gather. And you can see, of course, again, the match is not exactly, it's very, very perfect, but we are getting in there. And actually, we are, due to time limitation, I was running it on my laptop. These things are actually run, takes a lot of time to run, because these are all global Monte Carlo type of simulation. I was running it on my laptop, and I just stopped it, because I had to create my slides, so I just wanted to stop the job. If I had continued this one a little longer, probably it would have done a little better job. So, just now we are talking about, we talked about two issues in AVO and AVA, and one was the narrowband model, and another was the fundamental assumption. And now let's go and talk about another issue, which will basically, which will eventually lead us into the road ahead. And that issue is, when we are talking about this synthetic and real data matching, you see, we converted the offsets to angles. And how the offset to angle transformation is done right now, this is actually what is my third issue, is the optimal offset to angle transforms. This is basically the one which we use. It is the key element, whether you are using AVO or AVA based inversion or full waveform. At some point of time, you have to do somewhere, you have to do this, convert these offset to angles, because that is where we are matching. We are getting into the plane wave domain, and we are matching data with synthetic in the angle domain or P domain, the ray parameter domain, but it's essentially they are the same thing. And all the offset to angle transforms are approximate. So, and although we can make it to work in the presence of isotropy, it is very difficult to use this in anisotropy. First of all, the NMO in anisotropy is very complex. We have to use angle-dependent velocities. There is an issue, those angles, that reflections occur in phase angle. But when we do the offset to angle transform, those angles are group angles. So we have to really understand what is the difference between the phase and a group angle. That is another issue. So we have to handle that. We cannot apply this kind of standard, simple offset to angle transform when there is P wave, convertible. Suppose we want to do both P to P and P to S, mode converted events, and we have to invert together on like a multi-component inversion. And it does not work. It's not that easy to do an offset to angle transforms when we have converted wave data. And both AVO and AVA and AWI are based on this approximate offset to angle transform. And what we essentially do in this approximate transform, we start with an offset domain data, which is NMO uncorrected. We first correct it for NMO. We find my angle mutes. So we get constant angle zones and also a Fresnel zone, and then we partially stack all the offset traces between that and convert one angle, convert it to the angle. Then we again find another off angle trace, then another zone for partial stacking, get another. So by doing this, repeating it for different angles, we start from the NMO uncorrected offset gathers to NMO corrected angle gathers. This is exactly what we do. Now, what we propose to do is a new offset to angle transform, which is based on ray theory, which Arthur talked about it a little bit. We start straight on the NMO uncorrected gathers, and we ray trace using the group velocity, and as we are changing the medium, we go to the phase velocity and phase angle and try to get the correct reflection, refract the traces accordingly. And the advantage of this, we can handle dips very easily. We can get the both PP and PS gathers and display them both in either PP time or PS time. I'm going to show an example on an anisotropic model with that. And we can get it either on zero offset P wave time or zero offset S wave time. We can have any arbitrary anisotropy. Although the example I am going to show is a VTI type of anisotropy, but this methodology is not dependent on the type of anisotropy. I can have any type of anisotropy as I wish, and I can still ray test and get the group angle gathers or phase angle gathers, whatever I wish for. So essentially, this is what we do, is we just, from any time sample point, we fix the angle, a group angle or a phase angle, and we ray trace. So I can have one side can be P or another side can be S. So it really doesn't matter. And then we ray trace and find the offset on the NMO uncorrected move out and find out and fit a polynomial and stack and move it and get the angle. Now if I, from one angle, I ray trace, I get one part of that NMO curve. For another angle, I go to the another part of the NMO curve. I fit a different polynomial. So essentially, I can handle angle-dependent velocity by that process. So let me just give you an example. So although I am showing this for a horizontally stacked layers, that does not, it does not stop us from applying it to more complex, in the presence of complex geometry. So this is an example which Pradeep, who is also working with us on did it and he's just submitted this paper in geophysics. This is for a multi-layered anisotropic arc model. This is what a conventional P2P angle gather will give. And you can see this is bending upwards due to, because the velocity is not, see when you are doing NMO in an anisotropic model, you are using one velocity and then some complex relationship of epsilon and delta, but actually it is not correct. It is okay for small angles or small offsets, but rapidly as you are going to larger angles and larger offsets, that equation fails. So, and you can see that effect, it is bending upwards. Sometimes it also bends downwards, depending on your model. And this is the ray-based P2P angle gather, and this is ray-based P2S angle gather. And you can see both P2P and P2S are converted into two-way P-wave time. So this is actually still, we are working on it, and you can see some things here. Those are, I think those are bugs in the code. There are some, rather than the theory. So we are working on it, but I think we are going to get all these things fixed up soon.
And it's a 2D ray trace?
It's a 2D, and we can do it 3D.
So how are you going to sector that, or how are you going to gather your traces?
That we have to think about. We haven't really. This is just a proof of concept right now. We are completing a proof of concept, and what we have found is this ray trace angle gather is very sensitive to velocities. If you are using a velocity which is a little bit off, you get it is bent. So that could be used as a very nice velocity analysis tool. That is what we think. Yes.
I think there are any applications in microseismic data. They have a demo of the time to velocity models.
There is a possibility.
Yeah, I think you should try.
In fact, one of my DOE projects I am looking at is the microseismic for carbon sequestration. And maybe something we can try to do that. Yeah, thank you for mentioning that. So